It's my great pleasure to introduce my friend and colleague Vince Poor as our third plenary speaker. Vince is very well known for his research, teaching, and service contributions. He really needs no introduction at all, but since I have to say something, I'm going to go ahead and take a stab at summarizing his long and distinguished career. But of course, I can't say everything or we'd be here till tomorrow's Shannon lecture. So let me just touch on a couple of high points. Vince received his bachelor's, master's, and perfected his southern accent at the University of Auburn in Alabama. Then he moved north to Princeton for his PhD, which he received in 1977, after which he started his academic career at the University of Illinois in Urbana-Champaign. He stayed there until 1990 and then moved to Princeton. I've heard from Vince recently that he actually got the job at Princeton due to his incredible acumen in French wine tastings. So it's appropriate that we're here in France for the plenary talk. You can ask him about that later. He's been at Princeton since 1990, except for some short visits to England, Harvard, and fortunately for me, to Stanford a few times. He's currently the Michael Henry Strader University Professor of Electrical Engineering and Dean of the School of Engineering and Sciences at Princeton. I personally am very fortunate to have collaborated with Vince in several different research areas and on a recent book. And collaborating with Vince is like working with a whirlwind. It's amazing to me his really deep insight, his depth and breadth of knowledge, his competent and efficient administrative abilities, and the way that he can juggle so many balls and seem so calm while doing so. In research, he's spanned information theory, signal processing, control, and wireless. I think there's few researchers with so many profound contributions to so many fields. He's won just about every honor for his research, including election to the National Academy of Engineering. He's a member of the Academy of American Academy of Arts and Sciences, a former Guggenheim Fellow, IEEE Fellow, a Fellow of the Institute for Mathematical Statistics, and many other scientific and technical organizations. I think many people in this room know him for his outstanding teaching and mentoring. He's had dozens of PhD students, which are really a who's who of leaders of the field in research and in industry. Many of the people that have benefited from his mentoring and from his PhD advising are in this room, including tomorrow's Shannon lecturer. In teaching, he's also been recognized with many profound awards. He's won the IEEE Education Medal, the National Science Foundation Directors Award for Distinguished Teaching Scholars, and an Excellence in Teaching Award from Princeton School of Engineering and Applied Science. And he's also founding director of Princeton's Center for Innovation in Engineering Education. So he's really made many, many contributions to the teaching of engineering as well as research. Service, we all know Vince for his tremendous service to our community. He's also been of tremendous service to others. He's been our editor-in-chief for the last 3 years. He has 3 days and counting, so I understand. So get your papers into him quickly if you want Vince to handle them. He's been on the board of governors many times. He's been former president of our society. He was a Division 10 director of the IEEE Board of Directors, and he's also been on the board of governors for the IEEE Control Society. Vince's ability to balance so many things is truly amazing. Just in this past year, in addition to being our editor-in-chief and dean of the School of Engineering and supervising dozens of students and postdocs and writing dozens of papers and books, it's really mind-boggling to me how many things Vince can do and how well he does them. As Vixio said at the lunch yesterday, you send Vince an email and within about 2 picoseconds you get a long and detailed and important response. So I just want to make the point, Vince, that I think you actually do a big disservice to our society. By doing so many things so well, you really make the rest of us look bad. So I think you should slacken off a little bit. His title of his talk is Competition and Collaboration. in wireless networks, and I hope this doesn't mean that he's going to have more slides and more references and more collaborators than Shlomo listed in his talk yesterday. So with that, Vince.
Good morning. Can everyone hear me okay? So thank you, Andrea, for that really very nice introduction. I think some of it might have even been true. I think the part about the PhD is true. And Sergio, of course. So anyway, thank you very much. Thank you, and also your co-chairs for inviting me to give this talk. It's really an honor, and I'm really happy to be here this morning. So I'm going to talk this morning about some problems in wireless networks that have been interesting to me lately, and I hope you'll find them to be interesting. This is not going to be a comprehensive talk about the subject matter. Rather, I'm going to talk about two particular areas that, that I found interesting, and one of them is fairly well developed, one of them is more preliminary. So I hope you'll agree with me that these are interesting areas. By way of intro, let me just give a brief perspective, at least from my vantage point, of wireless research over the last 20, 25 years that I've been involved in it. First of all, certainly, I would say over the past 2 decades, maybe even a bit longer, there's been a tremendous amount of interest and major developments in the physical layer of wireless. And I'll just mention 3 here. MIMO, of course, or MIMO, depending on whether you're American or English or French. MUD, multi-user detection. Sergio is here today, the representative of that. And turbo, for example. So these are major advances in the physical layer that have made tremendous difference in the way we think about wireless networks at the link level. Now, more recently, and I would say roughly since the turn of the century, the focus has shifted a bit, although, of course, there are many, many interesting problems at the physical layer and continue to be, and will continue to be. But I would say the interest has shifted a bit from the performance of individual links to the interactions among the nodes of a network. And so I'll just mention a couple of areas that are very much in evidence at this meeting and other meetings of this type that are going on right now in Scotland, for example. Cognitive radio. I would say there's sort of 2 sort of modes of interaction, and these are the 2 modes I'm going to focus on today. One is competition, and examples of competitive behavior in wireless networks among nodes are cognitive radio, where you're competing for spectrum. Information theoretic security, we've heard a lot about that at this conference. Shlomo mentioned it yesterday. This is really a problem of competition where the intended recipient of a message is basically competing with an eavesdropper. And then there's been a lot of interest in the game theoretic modeling, analysis, and design of networks as well. And this is one of the topics I'm going to talk about today. On the other side, from sort of the opposite approach from competition, is the idea of collaboration among nodes of a wireless network. And I'll just mention a couple of examples again, which are very much in evidence here. Network coding, we heard in Michelle's talk Monday about network source coding. Of course, cooperative transmission and relaying. There must be dozens of sessions here on this. Multi-hop, this is a collaborative problem where also game theory plays a role in coalition games and so forth. Collaborative beamforming, more of a physical layer type thing, but where we need to collaborate among nodes to form a beam. And finally, collaborative inference, which is the second topic I'm going to talk about today. So all of these topics are areas which have arisen relatively recently in the community, and they involve, as you see, node interactions rather than link layer issues. So again, I'm going to talk about 2 things today, and these are things, as I said, that have been particularly interesting to me. This is not a comprehensive discussion of all of these ideas, but rather I'm going to talk about 2 things. One having to do with communication networks, and in particular, I'm going to look at multiple access communication networks, and talk about energy gains, which is a way in which terminals compete for wireless resources in a way to preserve their energy efficiency. So this is a game theoretic problem. And then I'm going to talk about another problem which arises in wireless sensor networks. And this is the problem of distributed inference. And this is a particular problem where collaboration is sort of the order of the day. So the first problem is fairly well developed, as you'll see. The second problem is a little more preliminary, and there's a lot of interesting questions and open questions in both, but I think in the second problem particularly there's a lot of interesting things to do. So let me start with this issue of competition in the MAC in the context of energy games. And I want to mention that this is joint work with my colleague Stu Schwartz at Princeton and one of our former graduate students, Farad Meshkati, who Andrea has also interacted with, and several others who I'll mention throughout the talk. But all of this work involves these two people. So let me, just to set up the stage, let's take a look at a multiple access channel. Let's think about the uplink where you have a number of terminals communicating up to an access point in a multiple access, with a multiple access protocol. So we can think about a network like this as being something like an economic system where the terminals are economic agents competing for resources in order to maximize their own utilities. In this case, utility has to do with getting data across the link to the access point. But because it's a multiple access channel, it's a competitive situation. That is, the actions of one terminal affect the utility or the ability of the other terminals to communicate to the access point. So we can model this as a competitive game, or non-cooperative game. And I'm going to look at the situation where we model the game, where the payoff of the game, that is the utility to the terminals, is measured in energy efficiency, that is bits per joule. How many bits can be transmitted across the link to the access point per joule of battery? So this formalism is not a new one. This has been proposed by a number of people, in particular, notably David Goodman, Narayan Mandayam, Roy Yates, and others from WinLab at Rutgers. And this is a very nice formalism for looking at such problems. In particular, we can think about a game of this type. We have K players, where K is the number of terminals that are competing to communicate to the access point. Each terminal, the kth one, has a set of strategies or actions and a utility function. The utility function of interest here is the energy efficiency, which can be measured as throughput divided by transmit power. And since throughput is measured in bits per joule, transmit power in, bits per second, transmit power in watts or joules per second, the units of this utility are bits per joule, or energy efficiency. Now, the transmit power is a very straightforward quantity, of course, but the throughput we have to model a little more carefully in order to have something analytically tractable here. So we can, for the kth terminal, we can define the throughput in this way. It's the rate, the transmission rate, R sub k, times the frame success rate. So this is basically the good put. And the frame success rate we can model as an instantaneous function f of the received signal to interference plus noise ratio, with the signal to interference plus noise ratio with which that user's transmissions are received at the access point post-processing, but before data detection. So this is, of course, an idealization. We know that the frame success rate is not exactly a function of the SINR, but this is a reasonable approximation, particularly for some of the receivers that I'm going to talk about in this talk. The nice thing about this model is that this allows us to abstract the physical layer into this function f. That is, we can lump the whole physical layer into f, except for the SINR. So f includes all the things you might think of in the physical layer, the modulation, the noise model, and so forth, the frame length, the packet length, and so forth. So because the SINR has got the power of user k in the numerator, and the powers of all the other users in the denominator, remember this is a multiple access channel, you can see how this is a competitive game. That is, if I turn up my power, I'm going to positively influence my SINR and negatively influence everyone else's. So this is really a game on SINR. Okay, so let's look at a specific example of this game. So let's suppose we're going to fix the uplink receiver to be a linear multi-user detector. Say a decorrelator or minimum mean squared error detector. And then the actions available to the user, to each terminal, are just going to be to change its power, or vary its transmit power to maximize its own utility. So this is a power control game. Now, it turns out that in this game, as long as the function f that determines the packet success rate is sigmoidal, that is, it looks like this, as there's a point to the left of which it's convex, to the right of which it's concave, then this game has a Nash equilibrium. That is, there's an equilibrium where no user can unilaterally improve its own utility. So it's a selfish optimum. And this is reached when each user chooses its transmit power to achieve a certain target SINR, which is given by the solution of a simple nonlinear scalar equation. So basically, for this problem, Nash equilibrium requires SINR balancing. That's the principle of Nash equilibrium here. Now, this problem in itself is quite interesting. There are a lot of, it's a unique, the Nash, you can show that the equilibrium is unique. There's some nice iterative properties. There's some algorithms you can devise to achieve it in a distributed fashion and so forth. But it's also very useful as an analytical tool. That is, we can look at the utility at the Nash equilibrium as a measure of the energy efficiency of the network. And then we can examine that equilibrium as it's affected by various network design choices. So that is, we can use this as a way of modeling energy efficiency in a network, analyzing it, and designing things to put in the network. So I'll talk about several things later, but let me just mention one thing that we can do, for example, is compare different receiver choices at the access point. So here, remember, I've restricted this situation here to the case where we have a linear multi-user detector at the access point. So we can compare receiver choices. We can, for example, just look at the classical match filter. We can look at the decorrelator, which is, of course, the zero forcing solution here. Or we can look at the minimum mean squared error detector. And we can, by comparing the Nash equilibria for those detectors, we can see how that choice affects energy efficiency. So to do that, let's look at this model, a simple, flat, single input, multi-output model. So each of the terminals has a single transmit antenna. The access point has an array. And between each pair of antennas, there's a flat channel, okay, with given channel gains. Now, so far I haven't really said anything about the signaling scheme or signaling protocol. Excuse me. But if we restrict attention to random CDMA in the large system limit, then we can take advantage of the Say-Handley results to write a closed form for the Nash equilibrium. So in particular, just recall, random CDMA is a situation where we use direct sequence CDMA and choose the spreading codes at random. Remember we have K terminals, if we let the spreading gain be N, then the load of the system is just the ratio of K to N, that is just the number of users per dimension. So it's a measure of spectral efficiency. And then the large system limit just refers to the case where both the number of terminals and the spreading gain go off to infinity with their ratio fixed. In this case, the variations in the SINR due to variations in the spreading codes disappear. Everything becomes a constant. And we can write the Nash equilibrium in closed form. And I don't have it to show you here, but the paper that I just mentioned, the Period of Transactions on Communications, has those formulas. So I just want to show you a couple things about Nash equilibrium for this case. So just take a look at this graph on the left. We show here average utility, remember that's bits per joule, versus load. So this is energy efficiency basically versus spectral efficiency in this network. And there are three receivers shown here. The green is for the match filter. The blue is for the correlator or zero forcing detector. And the red is for the MMSE detector. And for each detector, there are two curves. The lower one is for a single receive antenna, and the upper one is for 2 receive antennas. And you can see that there's quite a variation here in energy efficiency due only to the choice of this is the energy efficiency at the terminals, but the signal processing we're talking about here, or the receiver, the detectors that we're talking about here are being implemented at the access point. Okay? So, for example, you can see that the match filter doesn't support much traffic here with any positive energy efficiency at equilibrium. The decorrelator and the MMSE detector are much better. The decorrelator is limited to unit load because it has to zero force, so it can't really go beyond unit load. The MMSE detector is not limited to unit load, and in fact, if we add a second antenna, the MMSE detector is much better than all the others uniformly. So, for example, if you just look at load of 60%, you can see that, first of all, the match filter doesn't support any traffic at equilibrium. And the MMSE detector has gives roughly twice the energy efficiency at the terminals as the decorrelator, even though they both have roughly the same complexity. So that means essentially that for the same throughput or the same good put, the terminals can all, if the access point is using the MMSE detector, the terminals can all turn their power down by a factor of 2 and get exactly the same throughput, or have exactly the same throughput. So this tells us something about the importance of receiver design on energy efficiency. On the right, there's another, this also shows utility or energy efficiency versus spectral efficiency. Incidentally, note, of course, as you might expect, that these two, energy efficiency and spectral efficiency, are opposing quantities. That is, as the spectral efficiency goes up, the energy efficiency goes down, as you might expect. On the right, this is the energy efficiency versus spectral efficiency or load for the MMSE detector only. And this is for different numbers of receive antennas. So going up, it's 1, 2, 4, and 8 receive antennas. Now, on this curve, the vertical axis is logarithmic. Over here, it's just linear. So the James here are more significant than they might look compared to this. And in particular, you can see that, first of all, the loads, the supportable loads are very high with multiple antennas. And also, since this is logarithmic and we're doubling the number of antennas as we go up on these lines here, basically we see a linear relationship between energy efficiency and the number of, at the terminals, and the number of antennas at the receiver, which is not too hard to believe. If you look at the formulas for these equilibria, you do see the linear relationship. But this is somewhat like what we see in MIMO systems in general. For spectral efficiency, we know that there's a linear relationship of a sort between number of antennas and spectral efficiency. And here we see there's something similar going on here, although here we're talking about antennas at the receiver only, multiple antennas at the receiver only. Now you might be thinking, well, what about, why would we do competitive gain in a situation where we have an access point who could control the power? Well, first of all, we can look at the other kinds of equilibria. For example, we can look at the Pareto solution, which is the so-called socially optimal solution, where we look for an equilibrium in transmit power so that no user's utility can be improved without decreasing someone else's utility. Unlike the Nash equilibrium, which we saw is very easy to characterize and so forth, the Pareto solution is very hard to find. You have to use numerical techniques to find it. But you can also, unfortunately, show that the Nash equilibrium is not generally Pareto optimal. But it turns out to be quite close, and in fact it's provably close for the decorrelator and the MMSE detector, and I'll just show you an example here. I think this is a very faint line. I don't know if you can see that one. But this, again, is energy efficiency versus load. This is, again, random CDMA, single receive antenna. And there are 3 detectors here. One is the match filter in blue, the decorrelator in green, and the MMSE detector in red. And there are 2 lines for each of these. You can't see the 2 lines for the green one, but there are 2 there. The lower line is the Nash equilibrium energy efficiency, and the dotted line, the upper line, is the Pareto solution, the energy efficiency of the Pareto solution. And you can see that they're very close, except for low energy efficiencies. they're almost indistinguishable. For the decorrelator, they are indistinguishable, and for the MMSE detector, they're virtually indistinguishable until we get down to very low energy efficiencies. So you can see that even though we might think about doing something centrally here, from the point of view of analysis and modeling and so forth, the Nash equilibrium is much cleaner, and it's almost the same as the sort of more global centralized equilibrium. Let me just talk about a couple of other issues here. Obviously in wireless networks, we're interested in more than just throughput. We're often interested in quality of service. And so we can look at the issue of delay QoS in this same model. And I've got two models for it here, which I'll talk about briefly. So, of course, delay is often important in defining QoS of a source. If we assume ARQ here, then the delay, if we let X represent the number of retransmissions, or number of transmissions, it's going to, assuming they're independent, it's going to be a geometric random variable. And the parameter is going to be the frame success rate. So the delay here is related to the physical layer through this function f and through the SINR. So we can introduce a delay requirement here as a pair, d and beta, where d is the delay above which we would like to not go with at least probability beta. Okay? And because this is a geometric random variable, x, and because f is sigmoidal, this requirement, this delay QoS requirement, translates into a lower bound on received SINR. So in order to introduce a delay QoS in this model, we really have a constrained game to play. Not only do we choose the power, but we have to choose the power so that we achieve at least a given SINR that's going to allow us to achieve our delay QoS requirements. So we can divide the network up into heterogeneous classes, that is, multiple delay classes, where each class has all the same delay QoS requirements within the class. So that means that each class, say class C, is going to have its own SINR constraint coming from its delay constraint. So now we have a constrained game, multiple constraints. But this game also has a Nash equilibrium. And in this Nash equilibrium, again, the choices for the user are to choose transmit power. So we're still talking about a power control game. The Nash equilibrium occurs when all users in a given class SINR balance again, but now to the maximum of this target SINR gamma star from before, that comes from the physical layer through this function f, and the delay constraint. So the delay constraint comes from the network, right? This is the QoS constraint. So you can see that for a user with a delay constraint, if the delay constraint is tight enough so that gamma prime is larger than gamma star, the utility is going to be diminished from the optimal utility for that user, for that class of users. Because we have to, if we're going to meet the delay QoS, we're going to have to give up a little energy efficiency, basically, to do that. But because this is a multiple access channel, the delay constraints on one class are going to affect all the traffic, even the ones that are delay tolerant. Because if I have a delay constraint, I'm going to transmit more power, I'm going to interfere more with the other users. Even if they don't care about delay, they're going to be affected by my delay intolerance. So we can characterize this by looking at the loss associated with the delay QoS requirement. Excuse me. This is a two-class network. Again, we'll look at random CDMA and the large system limit. Alpha is the load, and alpha A is the load of a class A. So there are two classes. Class A is delay sensitive, so its delay requirement is that 99% of the time its packets get through on the first try. Class B is delay tolerant. It only cares that 90% of the time its packets get through on 3 tries. So up here we show the loss, or ratio of the utilities under delay QoS constraints to the unconstrained utilities from the previous case versus the fraction of users that are delay sensitive. So alpha A is just the load, delay-sensitive load. Alpha is the total load. And on the left, you see three receivers again. This is the match filter. Blue is the decorrelator. It's hidden behind the red, which is the MMSE detector. And then for each detector, there are two lines. The lower line is the loss relative to unconstrained case for delay-sensitive users. The upper line for each color is the loss for the delay-tolerant users relative to the unconstrained case. You can see that in this case, as the number of delay-sensitive users increases, or the fraction increases, there's significant loss in energy efficiency if you're using the match filter. If you're using the decorrelator or the MMSE detector, there's virtually no loss for the delay-tolerant users, and there's about a 20% loss for the delay-constrained users. Now this is for a like overall load, 10%. If we increase the overall load to 90%, then of course now the match filter doesn't support any traffic. We saw that in the previous example. But we can still compare the MMSE detector and the decorrelator, and we see that the decorrelator is really unaffected by load, or at least the relative performance of the decorrelator is unaffected by load. And this is of course because the decorrelator zero forces the interference. So it basically gets rid of that issue. Whereas the MMSE detector, as we have a high load, starts to lose some ground relative to the decorrelator in terms of tolerance to delay. We can also introduce queuing. We can assume that this is joint work with Radu Balan of Siemens, where we introduce the usual kind of model. We have Poisson arrivals, which are FIFO'd and a buffer, transmitted via ARQ over a multiple access channel. Now we can define QoS in terms of two parameters, average delay and source rate. So the source rate is going to be the packet arrival rate times the packet length. And the average delay is just the average delay across this length. So again, one can show through some analysis that this translates into a lower bound on SI and R. We again have a constrained game. We can now play a Nash game not only with transmit power, but also with rate on the air. So we can vary both the transmit power of each terminal and the transmit rate on the air in order to try to achieve with QoS in terms of source rate and average delay. And the overall payoff is still energy efficiency. Now here, something new comes in. This leads to the notion of the size of a user. That is, there's a way we can quantify how much of the radio resources a user needs to deliver a certain level of QoS. From that, we can see that in order to achieve a Nash equilibrium on this network, we must have a situation where the sum of the sizes of all the users is less than 1. So now you see there's an admission control issue. We can only admit users until their total size is equal to 1. The details of this can be found in this paper, which, by the way, is also on archive. But once we have achieved this, then there's a Nash equilibrium in transmit power and rate. So just to give an example, here's utility versus delay. Utility, again, is energy efficiency. Delay is average delay. These are both normalized in this case to be dimensionless. The utility is normalized by B, which is the bandwidth on the air, times the signal-noise ratio of the total bandwidth, and delay is normalized by multiplying times the bandwidth on the air. And here, this is the utility of a single user, where the combined size of all the other users is 0.2. Okay, so this user can be admitted until its size gets up to 0.8, which happens when we really tighten down the delay QoS requirement. So the horizontal axis here is the delay QoS parameter, and then the source rate QoS parameter is given here in terms of how much of the total bandwidth the source needs. So we can see that as we loosen up on the delay QoS, we get higher utility, as you would expect. If we tighten up too much, we can't support this user anymore. And as we increase the amount of the channel needed by the source, we also lose energy efficiency at the equilibrium. So we can analyze here the effects of these kind of parameters on energy efficiency. So I want to move on to the next topic, so let me just talk a bit about a couple of other things that we can do here, and I'll just do this very briefly. For one thing, we can go to nonlinear multi-user detectors. That is, we can, in all this analysis, I assume that when you're using a linear multi-user detector, well, we can actually, as long as we want to restrict, or willing to restrict ourselves to random CDMA and the large system limit, we can also apply the same results to a number of nonlinear multi-user detectors, like maximum likelihood, maximum a posteriori probability, parallel interference cancellation, and so forth. This is with joint work with Dong-Min Guo, which will appear in the transactions on wireless. Essentially, you again get equilibria, which are SI and R balanced. It's interesting that now we can compare, say, the maximum likelihood detector to the MMSE detector in terms of energy efficiency, and the maximum likelihood detector being the gold standard of multi-user detectors. And interestingly, you don't gain much in energy efficiency by going from the MMSE detector, which is the most efficient linear detector, to the maximum likelihood detector, which is essentially the most efficient nonlinear detector, unlike other things, in error probability and so forth, where you do gain a lot. And of course, maximum likelihood requires much higher complexity, so from the point of view of energy efficiency versus complexity, the linear detectors are probably better. We can also look at the multi-carrier case, where the actions include the choice of a carrier in addition to the choice of transmit power. This is joint work with my colleague Meng Chang, which has appeared in a JSAC special issue last year on multi-carrier. And so it turns out here that, interestingly, to achieve spectral efficiency with multiple carriers, of course, you do water filling, something like water filling, right? But to achieve energy efficiency, you want to choose a single carrier and put all your energy on that one carrier. So it's a different design criterion or a different design philosophy that this leads to relative to spectral efficiency. We can also look at ultra-wideband, where now the issue of rich scatter comes in. We have to look at a lot of multipath. Here we can look at other asymptotes involving the channel order. Let the channel order go to infinity as the gain goes to infinity. The processing gain goes to infinity. This is for impulse radio. And again, you get some interesting things. Here you have self-interference and so forth. This is joint work with Giacomo Bacci and Marco Luisa of Pisa and Antonio Tolino of Naples. This is going to appear in a special issue of the journal, a new journal, the Journal of Special Topics in Signal Processing, a special issue on UWB. And then finally, we can talk about adaptive modulation, where we now let the terminals choose their modulation index in QAM, say. This is in joint work with Andrea. That's going to appear in a JSAC special issue later this year. Here, as you might expect, again, contrary to what you would do for spectral efficiency, you want to choose the lowest order modulation index that you can and still achieve the QoS target. Okay. We can also do waveform, adaptive waveform selection for CDMA systems. This is joint work with Stefano Buzzi, which was presented at the European Wireless Conference in Paris in April. And here, now you can start seeing orthogonalization going on when the load is less than 1, and then when the load gets greater than 1, you have to worry about the interference at that point. So there's a lot of other interesting things I could say about this problem, but I want to move on to the next problem. I'll come back to this at the very end briefly. And I want to talk now about the problem of collaborative inference. And I'm going to shift to another type of network, wireless sensor networks. So this is joint work with my colleague Sanj Kulkarni and one of our recent graduate students, Joel Pred, who's now at RAND, and other people who I'll mention in the course of the discussion. So of course, wireless sensor network, you think about something like this, where you drop a lot of sensors out at random. They start collecting data, and the goal is to do some detection and estimation or mapping or something like that. The sensors have to communicate wirelessly, and typically they have very limited resources to do so. So these are really the salient features of wireless sensor networks. So first of all, unlike communication networks and sensor networks, the application is primarily inference, that is, detection, estimation, and mapping. In other communication networks, the application could be all sorts of things. Web browsing, talking on the phone, and so forth. Another important feature of wireless sensor networks is that the information at different terminals is often correlated. That is, the sources are not independent. If you drop sensors at random and they're measuring some physical quantity, then two sensors that are close together are likely to have highly correlated measurements. So source correlation is a salient issue in sensor networks. And finally, energy is often severely limited. Now, in communication networks, or in all wireless networks, energy is always limited. But in contrast to, say, a cellular network or a Wi-Fi network, sensors usually deployed in places where humans don't want to go or don't often go. So you can't recharge the batteries or replace the batteries easily in a sensor network. It's not like a cell phone that you can plug in every night. So even more so than other wireless networks, energy is much more of a concern in sensor networks. So I'm going to talk now about this the first issue, inference, sort of driven by these other two issues. And so, what is collaborative inference? Well, collaborative inference is when sensors work together to make inferences, trying to conserve the resources of the network, that is, batteries and bandwidth. And I'm going to look particularly here at the problem of collaborative learning. So just by way of background, I'll just say a bit about the classical supervised learning problem. This will inform what we're going to talk about in a minute. So the basic setup is the following. We have an input space, or this is often sometimes called an observation space, which is the set of real vectors of dimension d. And we have an output space, which is just the real line. And then we have, so pairs of inputs and outputs are just x, y value random variables with some joint distribution. And we'd like to design a function f to predict outputs from inputs, okay, or to predict targets y from observations x, in a way to minimize some expected loss. So, for example, mean squared error. And of course, if we know the joint distribution, the solution is the conditional mean, and we're done. But in many applications, certainly sensor networking, where you're putting things out in some unknown territory, the joint distribution between x and y is unknown. And so we want to use learning to construct f from examples or exemplars, which are just which are sets of inputs marked with correct outputs. Okay, so that's the classical supervised learning problem. Now we want to look at sensor networks. So suppose we have a sensor network, sensors thrown out at random, and we can think about the exemplar. So we think about this as a distributed sampling device with a wireless interface. The way to think about a sensor network in this context. And we can think about a situation where each sensor measures some subset of the exemplars. So the exemplars are somehow distributed around in the network. They're not all in one place. Of course, in classical learning theory, all the examples are together, and there's a tremendous number of results in this area, all sorts of interesting things you can do. But what if the exemplars are not collected together, but rather they're distributed throughout the network? So this distribution is going to define a topology, and that's going to shape collaboration in this network, as we'll see. So first of all, let's go back. What would we do if we had all the examples collected in the same place? They weren't distributed. Well, one approach is to use kernel methods. That is, the sensors, say, send all of their examples back to some centralized processor somewhere and forget about them. The centralized processor takes them and tries to synthesize the function f using least squares, a least squares fit, within where we choose the function to be within a reproducing kernel Hilbert space defined by a particular kernel of interest. Okay, so this is a sort of a classical kernel method of regression or of learning. And we, in addition to the least squares term, we penalize the norm, the RKHS norm of the function f. So there's a penalty constant lambda, norm penalty, least squares, and this is sort of a classical kernel method for estimating the function f from the exemplars. So we're going to assume now that energy and bandwidth constraints preclude the sensors from doing this. That is, the sensors can't send their data all the way back to some central processor, and they're going to have to cope with the data locally. So this gives us the seed of a model. Since we have the distributed data, if you will, is distributed according to some physical sensor network, we can think about neighborhoods, and we can think about a situation where sensors can access neighboring sensors' data. So the justification for this is the usual one for distributed networks, is that local communication is efficient. And certainly in wireless networks, that's true. We can communicate with our neighbors much more cheaply in terms of energy than we can, and bandwidth than we can communicate with a distant access point. So this gives rise to a model like this, which is a fairly general model that applies to that situation and many others, as we'll see. So we can think about a model like this for this kind of problem, where we have a number of learning agents, M, which here in the sensor network example are sensors, and a number of training examples, N. And so we can think about a bipartite graph here, where the learning agents are the top part, the training database is the bottom part, and the edges exist between a learning agent and a training datum if that learning agent has access to that data. Okay, so this is a general way of looking at distributed inference. So, for example, centralized processing is the case where we have one learning agent and there's an edge to every exemplar. Spatio-temporal field estimation. This is sort of the sensor network problem, where we can think about some geometric structure on the exemplars that are out there. And the sensors have access. That is, the graph is defined in terms of the physical proximity. We could also think about other examples, where, for example, where we have a public database. So each of the learning agents or sensors has its own examples, and it has access to some published database. Maybe it's in the case of a sensor net, maybe these are some examples that can broadcast out to everyone. Or this could apply also to medical records and all sorts of other examples. But generally, we don't need to worry about what particular case we have. We can just think about a general bipartite graph of learning agents connected to a training database. So with such a model, how can we set up learning? Well, a natural thing to do is to do local learning. That is, let each of the learning agents learn according to a kernel regression applied to its own, to those exemplars to which it has access. So, agent 1 has access to these 3 data points. It does a little kernel regression on those 3, and it gets an estimate of the function f, which we'll call f1. And each learning agent does that. Okay, so each learning agent now has a local model for what's going on in the whole field. The problem with local learning is that it turns out to be locally incoherent, typically, okay, usually. That is, if, say, 2 learning agents examine the same datum, we'd like them to be consistent or coherent, so-called coherent on that datum. That is, we'd like them to have the same view of what the model is on at that data point. Okay? But it turns out that with local learning, you don't get that. That is, typically you have incoherence in local learning. Provably incoherent. But it's good because it requires only local communication. In the sensor network case, we only need to look locally to do our inferences. But local incoherence is bad, and that's because you can prove that if you have locally incoherent inferences, that there's a locally coherent set of inferences that's better. Okay? So it's undesirable to have local incoherence. So we might ask the question, is there some way for the agents to collaborate to get rid of this local incoherence while retaining this efficiency of locality, that is, without having to communicate more broadly than its neighbors? So one way to set that up is to start out with local learning. That is, we go through the sensors, or the learning agents. Each one of them performs a kernel regression locally. But rather than stopping there, it then, a given sensor, after performing local regression, updates all of the data points to which it has access with its own estimate of the targets, estimates of the targets. And we can iterate through the sensors and updating, and then we're going to get some consensus among on the shared data. Now we need to change this slightly because we're going to have to iterate over time in addition to iterating over sensors. And to make things work, we want to add an inertia term. That is, when we iterate at time t, we'd like to be sure that we penalize the difference between our kernel regressor at that point, a kernel regression estimate at that point, and the one at the previous time point at that sensor. So we add an inertia term, we have this least squares term. We go through sensor by sensor, updating the database as we do, and then we iterate over time. So we have an algorithm something like this. This is the same thing repeated. This was presented here in Uruguay. You may have seen this presented by Joel. We've done some more analysis on this algorithm now, and we have a paper submitted to the transactions. And you can show a lot of nice things about this algorithm. So just back in the context of this graph, basically what we're doing is local kernel regression with message passing. That is, we're updating. Once we regress, at a given time, in a given sensor, we find our estimate of the field F. We then update the database, then we move to the next sensor, and so forth. And then go through all the sensors over multiple times. Well, this algorithm has some nice properties. It converges in norm to a relaxation of the centralized kernel estimator as we iterate longer and longer. The limit is locally coherent, so it doesn't have that problem that I mentioned before. And also it lies in the span of a finite number of functions. So actually the estimation we're doing is just estimating coefficients. It's very efficient. Also we get improvement with every update. And if we have a connectivity property of the network, this is true of any topology, no matter whether it's connected or not. But if we have a connectivity assumption, and we have IID exemplars, and the lambdas, remember these are the penalty coefficients, have certain asymptotic behavior, then the local estimates converge in our KHS norm to the conditional mean, that is the global estimator, as the number of exemplars goes to infinity. So this algorithm has very nice properties, asymptotically. So I'll just wrap up with a couple of examples. This is an example, and then I'll take questions. This is an example where we have the observations are one-dimensional. They're uniformly distributed in -1 to 1. They're 50 sensors. We observe the field plus noise with IID Gaussian noise. There are two cases, one in which the function f is linear and one in which it's sinusoidal. Neighborhoods are defined by physical proximity or a linear proximity by a parameter r, the radius of the neighborhoods. And in the left-hand case, the sensors employ a linear kernel. The right-hand case, they employ a Gaussian kernel. You can see, as you might expect, that the mean squared error improves as the radius of the neighborhoods gets larger. That is, as we include more and more things in each sensor's neighborhood, we get better and better performance. Here we have 3 algorithms shown. This dark line here is centralized processing. The top line is local only. And this line is this message passing algorithm I just showed you. This is for linear, and this is for sinusoidal. You can see that sinusoidal is not quite as, doesn't work quite as well, but the linear kernel completely captures the linear function, so that's why the behavior is this way. I just want to mention one last point about this, and then I'll wrap up. You can see that the overall error decreases as we let the neighborhoods get larger. But of course, with message passing, the energy consumed is also going to increase as we let the neighborhoods get larger, because we have to traverse greater distances to reach all our neighbors. So we might ask the question, what is the trade-offs here? And I'll just give a very simple example. This is really preliminary, just to show you that there is really a trade-off between performance and energy efficiency here. This shows mean squared error versus number of sensors for those same 3 algorithms, centralized, the message passing, and local averaging, for 4 different growth rates of radii. Here we're letting the number of sensors grow. It should be small then. The number of sensors is growing at a power of the radius of the neighborhoods is growing at a fractional power of the number of sensors, 0.33545, in the both local averaging and PKP. And we see that, as you might expect, centralized is best as the number of sensors goes up. The 4 bottom lines are these 4 message passing algorithms in order of radius size, largest being the smallest MSE. Local averaging is not as good. The green lines are overlaps between local averaging and message passing. But in terms of energy efficiency, we get a different picture. This is the same set of algorithms again. This is energy consumed for communications per sensor. Very simple model, no multi-hop or anything like that, just overcoming the diffusion losses. Centralized, of course, doesn't matter how many sensors per sensor, the energy is the same. This is a randomly distributed network. For the local averaging, we always save energy, you might expect. But for the message passing algorithm, if the radius doesn't grow too large, we save energy. But if the radius grows too large with the number of sensors, we actually cost more energy to pass messages than it does to just send everything back and let the central processor handle it. So this is sort of a cautionary example. It's really very simple and preliminary, but it just shows that when thinking about local processing and local communications as being a way to save energy, there is more to think about in that kind of situation, because if you communicate enough locally, it might have been better to go ahead and just communicate globally in the first place. So let me just mention a couple of related results and then I'm done. We can also look at another problem like this where we have sensors who don't collaborate but who communicate back to an access point on very limited capacity links. And we can ask questions of consistency and regression and classification. And it turns out that we can get consistent regression with very low, and classification with very low communication capacity constraints. This is very low communication capacity. This appeared in the transactions last year. Another interesting problem is collaborative beamforming, where sensors that cluster together can get together and form a common message and then form a beam on the access point. It's another way to save energy. And we can analyze this properties of such beams. There's no information theory in this. It's just all signal processing. But this is in a paper that appeared in December '05 in the signal processing transaction. And then another problem is judgment aggregation. I mentioned this problem of local incoherence. This is a problem that also comes up in all kinds of applications of panels of it, combining the judgments of panels of experts, like review panels, for example. Psychologists worry a lot about this problem, and Joel and Sanj and I have worked with a psychologist, Dan Osherson, to come up with some general algorithms for judgment aggregation for general cases, and this is in a preprint. So With that, I think I'll just give a brief summary. We looked at two things: competition and energy gains, where we can characterize the energy efficiency of networks via Nash Equilibrium. It's a very useful tool for looking at that issue in wireless networks. We looked at sort of some preliminary results on distributed inference, where we can think about collaboration among terminals and nodes as being message passing. And with that, I'll thank you and take questions.
We have time for a couple questions. Any questions for Vince?
It was either crystal clear or totally opaque.
I have a question. I just need a clarification in the here.
Oh,
Okay.
hi, Ali.
Yes, in the message passing algorithm that you described, so how
Yes.
do you update the data points that are shared between multiple sensors?
Yes, pardon? What was the question?
When you have data points that are shared between multiple sensors,
Yes.
you call them L1, L2, L. So
Yes.
how do you update that data point?
Those data points are they're updated sensor by sensor. So when a sensor does its regression, it updates everything. This is done sequentially among sensors. So a sensor does a regression, it updates all the data points that it's connected to. And you move on to the next sensor and it does it again. And the order it's actually robust to order. You get the same asymptotic properties regardless of order, so it's robust to order. That's a good point. Other?
Any more questions? Okay, let's thank Vince
Thank
again.
you very much.